So yeah, first off, thanks to Alex and Carlos for inviting me to talk here. I'm going to talk about some work I did together with Carlos while I was at Georgia Tech on the low energy collective modes of two-dimensional Fermi gases. And I'm glad I'm doing this talk later in the week because there were already some good introductions about Fermi gases and two-dimensional Fermi gases. So I can just mostly focus on the results and I don't give too much of an introduction into the system we're studying. So as I did this work together with Carlos, I'm taking a page out of his book and I'm going to start with the main results, so the conclusions. So we're studying the collective mode in two-dimensional Fermi gases, and the main result can be captured in a figure. So what I'm showing here is the energy dispersion of the collective modes in two-dimensional Fermi gas, which we can numerically solve for, and it's the red line I show here. So it's the collective mode dispersion in function of the wave number. And I show this for different values of log KFA, where log KFA, so A is the S-wave scattering length, the two-dimensional scattering length, which controls the interaction. So on the top left, it would be in the Bose regime, while on the bottom right, it's in the BCS regime. And we can calculate the collective mode dispersion for all values of this parameter. And so the main conclusions that I will talk about today is, first of all, that it's to obtain this red line that I show you, it's crucial to include quantum fluctuations of both the phase and the modulus of the order parameter. Otherwise, you get unphysical results. Secondly, just as in 3 dimensions, there's this change in concavity that occurs if you go from the Bose regime to the BCS regime, and we're able to find some analytic results about this concavity and how it changes with respect to the interaction. Then a crucial difference from the 3-dimensional case is that, so the blue line that I show here now is the 2-particle continuum. So above this line, it's energetically more favorable to break up pairs instead of exciting the collective modes. And in 3 dimensions, at some value of the wave number, the collective mode hits the 2-particle continuum and some damping occurs. In two-dimensional, this never happens. So the collective mode remains undamped for all values of the wave number, and this is due to the fact that the two-body bound states always exists in 2 dimensions. And finally, the maybe the most visual conclusion is that we found very good agreement with recent experiments, and we saw the talk of Henning Moritz earlier this week, where he also showed this figure. So they had some Bragg spectroscopy experiments in 2-dimensional Fermi gases, which inspired this study. And you can see that if you look at the dynamical structure factor, which is the black pixels I show here, that the maximum of this, so our theoretical prediction follows closely the maximum of this dynamical structure factor, and this is without any fitting parameters. It's just the theoretical result. So we were very happy to see such nice agreement with these recent experiments. So maybe a little bit of motivation. So why are we studying this collective mode? It's mostly because it's related to the spontaneously broken symmetry. So according to Goldstone theorem, there's always this Goldstone mode, collective mode in the system, and it's interesting to study in all kinds of different fields, from condensed matter, high energy physics, astrophysics, nuclear matter, and atomic physics. As by now you all know, it's interesting to study this in atomic physics because a lot of experiments can be done and they're in a really controllable way. And two dimensions are interesting because superfluidity there occurs through this Berzesi-Gosterwitz-Thouless transition. And if you look at high temperature superconductivity, and again, Henning Moritz talked more about this, but you see that a lot of superconductors that work at relatively high temperatures tend to favor some kind of two-dimensional structures. So it seems that superconductivity favors the two-dimensional structure. So because of this, a lot of experiments have been done on this topic as well. So in two dimensions, I'll go quickly over this. So superfluidity has been observed. The BKT transition has been measured. First and second sound, which we heard about earlier this morning. And then finally, also recently in Henning Moritz's lab, collective mode spectrum was measured, which were the experiments I showed you on the previous slides, which inspired this this study. So a little bit of theory. So we're studying the collective mode in atomic gases, so in two-component Fermi gas with S-wave contact interactions, for which I show you the Hamiltonian here. So the most important thing is this 4-point contact interaction, which we can rewrite using the Haber-Šatonovich transformation by introducing some pairing fields that I call phi here, which can be used to rewrite the 4-point interaction into coupling between fermions and a bosonic pair field. Then the fermionic degrees of freedom can be integrated out, and you get an effective bosonic action for the pairs. And then this pair fields, the effective action you get is intractable. So what is usually done is to expand this pair field around the saddle point. And I do this here in terms of its modulus and its phase. And you can expand for small modulus and phase fluctuations to get some Gaussian action, which you can, which is something you can really do something with, and the result is something like this. And the most important feature of this model is this M matrix, which can be seen as the inverse pair propagator. Show the equations here. It's same formalism as you would do in 3 dimensions. The main difference is that you get a 2-dimensional integral now instead of 3 dimensions, with here psi k is the energy of the free fermions, and epsilon k is the energy of the quasi-particles. Maybe the most important feature here is that you can see that there's this branch cut in this M matrix that starts at the 2-particle continuum. So when the energy is large enough to excite two quasi-particles, it's energetically more favorable to break up a pair instead of exciting collective mode. Because it's a Gaussian model, you can integrate also the bosonic degrees of freedom to obtain the thermodynamic potential, and from this you can calculate the equation of state to relate the parameters of the theory, which are the chemical potential mu and the order parameter delta, to experimentally more relevant parameters such as the two-day scattering length A and the density. The scattering lengths can also be related to the binding energy epsilon B. And there's usually two ways to do this. The easiest way is to forget about these Gaussian fluctuations and just only use the saddle point result. And in 2 dimensions, this is especially nice to do because you get these nice analytic formulas for the chemical potential and the order parameter in terms of the binding energy and Fermi energy. So I'm showing this here. The most relevant parameter in the theory is mu over delta, which controls the interaction. But of course, in experiments, they would rather change log KFA or the S-wave scattering lengths. And the thing is that in 2 dimensions, it's really important to actually do include these Gaussian fluctuations, especially in the Bose regime. So to do that, you would also take into account into the density equation the Gaussian thermodynamic potential. Then, unfortunately, you cannot find an analytic solution for the chemical potential anymore. But if you look at the result here, which if you include Gaussian fluctuations, you get this red line, and you can see that the big difference is really big, especially in the Bose regime. So it turns out, and this is especially important if you look at the collective modes, that you really need to take into account Gaussian fluctuations in order to get some physical results. In the BCS regime, you can use the saddle point result, but in the Bose regime, it's really important to include the fluctuations. So before I move on to the results, I want to look at this fluctuation matrix a bit more in detail. And as I said, it acts like the inverse pair propagator, and it's useful to look at it in the long wavelength limit, where again we can study it analytically. And so if you would invert this matrix, you get the propagators of the phase and the amplitudes and the mixing terms. And you can see that it has a pole which describes the collective modes frequency in the long wavelength limits, and so you see it's just linear. So it's a phononic mode with c being the speed of sound. And the reason why I'm showing you this is to show that apart from just taking quantum fluctuations into account, you also really need to include both phase and modulus if you want to describe the collective modes. Because if you look at the mixing terms, which are controlled by this chi theta lambda, which I show here in the with the red line, again changing the interaction, and you see that again if you go to the Bose regime, it's this mixing term becomes really important. So it's sometimes in theories they're only looking at the phase fluctuations, but in the Bose regime this is incorrect. You really need the mixing of the phase and modulus to correctly describe the system. Finally, outside of the long wavelength limits, you can numerically solve for the collective mode dispersion by looking at the poles of this fluctuation matrix, or equivalently look at the zeros of the determinants of this matrix. And as I said before, you can always find a solution to this in 2 dimensions below the 2-particle continuum. The 2-particle continuum is defined like this. So it's the minimal energy needed to excite 2 quasi-particles. And the reason why in 2 dimensions you can always find the solution is because a 2-body bound state always exists, and you can show that you can always find a solution because at this 2-particle continuum, if you would plug this into the M matrix, the phase component will always diverge at the continuum. So you can never find a solution there. So that's why there's always this repulsion between the 2-particle continuum and the collective mode in 2 dimensions. So now on to some results, and I'll again first start at the long wavelength behavior, where the collective mode dispersion is just linear, with c being the speed of sound. And again, 2 dimensions are nice because you can find these simple analytic solutions. And if I show this on a figure, I want to highlight again here the importance of including quantum fluctuations of both phase and modulus. And so the first dotted line I show here is the results you would get if you if you calculate the speed of sound using only phase fluctuations, which clearly gives some physical results in the Bose regime where it starts to diverge. Of course, we can do better than this, and we can include also modulus fluctuations. And if you do this at the saddle point level, this has been known for quite a while, you get this constant 1/√2 result for the speed of sound. However, in the Bose regime, we do expect to find Bokolyubov modes. So we expect to find that the speed of sound goes to 0 in deep Bose regime. And so this problem can be solved by including the Gaussian fluctuations to the equation of state. And if you do this, you get a more physical result, which I show here in the red line. So just to show that it's really crucial to include quantum fluctuations of both phase and modulus. And I can also compare here with some recent experiments where our calculation actually nicely agrees with experiments in 2-dimensional Fermi experiments. Now, of course, we can do better than this. We can also include higher order corrections to the collective mode spectrum, where the first correction would be a cubic term. And as we've heard in Yvan Castin's talk, these corrections can be important to describe, for example, damping processes. And again, we find some analytic results in terms of this ratio between the chemical potential and the Orton parameter. And it's this gamma parameter that that describes the concavity of the collective mode. So I'm showing these two parameters, dimensional parameters, gamma and eta, here again in terms of the interaction. So gamma is the most important one here. I again show the results for the different approximations where the dotted green line would be only phase fluctuations. The blue dashed line is phase n modulus fluctuations, but using the saddle point equation of state, and then the red line is with the Gaussian fluctuations included. And you see that this gamma changes sign at some point. So in the Bose regime, it's positive, which means that the dispersion would be supersonic or convex, while in the BCS regime, gamma becomes negative and you get a subsonic dispersion. For eta, the main difference with the three-dimensional case is that eta, so the quintic correction in 2 dimensions is always negative. So then I can finally come back to my main results, which I show here again. So the red line here is now the numerical solution for the zeros of the determinant of this M matrix, which shows the full collective mode dispersion at the Gaussian level. And I can add a few lines now. First, again, to show that it's crucial to add both, to include also modulus fluctuations of the order parameter, because if you would include only, if you would try to calculate the collective mode for only phase fluctuations, you would get the magenta dotted line, which especially in the Bose regime is incorrect and can lead to some unphysical results. Then we have some analytic results in the long wavelength limits, where the yellow dashed line here shows just the linear dispersion, which is controlled by the speed of sound. And then if you add the quintic term, the cubic term with the green line, you can see that the concavity changes if you change the interactions. And then if you look at the two-particle continuum, the red line never crosses the two-particle continuum because the two-bound state always exists. And so at the Gaussian level, the collective mode is undamped for all values of the wave number, which is a crucial difference with the three-dimensional case, where in 3 dimensions in the BCS regime, the collective mode dispersion would hit the continuum at some value of some critical value of the wave number and become damped. And then to conclude, I can again show the comparison with the recent experiments where we find this nice agreement with Bragg spectroscopy experiments that were done last year. So if you want to read more, you can scan the QR code or go to the paper on archive. And if you have any questions, feel free to ask.